Okay, so a little short piece here on areas of triangles, essentially it's sort of an application of law of sines. Not really, it's something that kind of comes up when you're talking about law of sines. Because usually when you think of finding the area of a triangle, you think half base times height, and very reasonably so. Area 1/2 base times height for a triangle. And the only thing that really defines base and height is that they're orthogonal to each other. They're perpendicular to each other. So, we could call this the base and that the height. But, if you've got a different triangle, you can call that the base and that the height because they're, again, perpendicular to each other. But you could also call that the height and that the base. Or that the height and this the base. As long as they're perpendicular to each other, base and height are fine. The trouble is, in a lot of applications, we either don't know or it can be tough to find what this height is. For example, if you just had, say, a physical object, you've got some triangular piece that you're trying to figure out what the area of it is. And, you can measure that this is 7 inches and this is 5 inches and this might be 9 inches. But measuring this altitude accurately is kind of tough because you need to get that angle just right. Because if you're off by a bit, then you're going to get a longer height and a larger area than you're supposed to. So it's not always convenient to talk about that height value or that altitude value, either because we don't know it, because it's hard to measure, or for whatever reason. But if you remember, when we were building law of sines, we took that height and made an argument about this kind of smaller triangle, that the sine of that angle alpha was equal to that height over c, so that height is c times the sine of alpha. So if we don't know this altitude, but we either know or can find one of the angles, instead of having to calculate that altitude, we can use our trig, and in this case we'd have to use that alpha and say that 5 or the 9 if we want to. Notice this alpha and that c are not opposite pairs. That c is one of the sides that makes up the angle. So as long as we can find that, then we have a nice way to find what that altitude is. And instead of using that height, we can adjust our triangle formula 1/2 base times that height as c times the sine of alpha. So it gives us a nice way to find area without having to find that height. And we might be thinking, well, finding angles is not necessarily easier than finding that height. But because ideally we have our different side lengths, then if we need to calculate this angle with something bigger, we can use law of cosines to calculate that angle if we want to. So even if all we had were these lengths, we'll talk about another tool that can handle this in a minute, but even if all we have are those lengths, law of cosine will give us an angle, and we can still use this tool. You'll often see this area of a triangle formula written as 1/2 BC sine A, using the A's instead of the alphas. And I like that, again, mostly because it illustrates that this angle is not the angle opposite of either of those B or C. Sides B and C make up angle A. These sides B and C make up that angle A, not that angle A being opposite. We're kind of ignoring that opposite side when we talk about this area. Now, this other argument here is just making a geometric argument like, well, what if this height isn't inside? What if it's outside? Does the logic still work? And it does. It builds the same tool. So there's a little fiddliness in it, but it's they're the same angles because we talked about that with law signs. There is a nice set for it for dealing with it being outside, but it builds the same tool anyway, so it's not something we worry about. But if you want to play around with it, have fun, play around with it. So the nice thing, somebody hands us a triangle, and we know one of the angles, let's say that's 35 degrees, and we know the two side lengths that make up that angle. Finding this area is very nice. The area of the triangle is 1/2 4 times 7, doesn't matter what order we put them in, times the sine of the angle between them. So is that 14 times the sine of 35 degrees? And, technically that's a nice exact answer, but if you want approximation, 14 sine 35 degrees, and we get 8. So the area of that triangle is 8, and if these are inches, do be careful, because this is 8 square inches, because we have inches times inches. So it's a very, very nice tool for area, often easier to deal with than, like, we could have used this to calculate that height and then plugged that into half base times height, but that's, it's an extra couple of steps. Having this in your kind of bag of tools for area of a triangle, half base times height if we know the height, but half BC sine A if all we have are side lengths and angles. And, again, you'll see a lot of books do this. It doesn't matter how you're labeling the sides and the angles, as long as it's the two legs that make up the angle, the two sides that make up the angle, the two sides that make up the angle. No opposite pairs going on. So that's our tool. So area of a triangle, and we're told that our A is 3 and our B is 4, again arbitrary labeling, that angle C just has to not be either of these angles, it's got to be the one in between it, so not opposite the A, not opposite the B, so this 30 degrees. And honestly, if it was, say, like we only knew this side length, well, then we have an opposite pair, so law signs can take over and tell us anything else we want. So if we don't have this set up perfectly, the two sides and the angle between them, we can use law cosines or law signs to build any of that other information that we want. But as long as we eventually get down to this structure, the two side lengths and the angle they create, then our area is going to be 1/2 the product of those side lengths times the sine of the angle between them. So 1/2 times 12 sine of 30, I'm not even going to count, that's 1/2, we know that. So half of that's 6, and half of 6 is 3. Oops. So our area is 3, whatever the units are, squared. So, It's a nice tool. Determine the area of the shaded region. Okay, so we want the area of this nice shaded region. Well, we've got a triangle here. Got a radius of 5. That means both those lengths are 5. Well, probably the nicest way is to find the area of that sector and subtract, oops, the area of the triangle inside it. Luckily, we had a tool for finding the area of sectors. The area of a sector, you may remember, was what, 1/2 theta r squared minus the area of the triangle, which would be what, 1/2 of 5 times 5 times the sine of 80 degrees. So let's go ahead and do that triangle real quick. That triangle would be 25/2 times the sine of 80 degrees, which, if we want a decimal approximation, this is our new tool here, so do that one first. 25 divided by 2 is, of course, 12.5 times the sine of 80 degrees is, what, 12.31? 12.31, area of our triangle. Now, we do have to be a little careful. We know that this tool for area of a sector is dependent on us being in radian measure. So we do have to convert that 80 degrees into radians if we want to use it. So cancel out the tens, divide by 2, so 4 pi over 9, so 1/2 times 4 pi over 9 times 5 squared is, divide out those 2's, so 2 pi over 9 times 25, or how about 50 pi over 9, area of the sector. So 50 pi over 9, just to get a decimal approximation for that for comparison, 17.45. 17.45 is the area of our sector. So subtract the area of our triangle. So I'm going to subtract, oops, subtract do it and get 5.14. And it was 5 centimeters, so these are both square centimeters. So 5 square meters, 5.14 square centimeters is the area of that little shaded region. So a nice reminder or application for area of a sector, but then subtract the area of that triangle, and we can get that nice little hidden section. That's kind of a fun little problem. Now, I did say there was a tool if we happen to have all the sides of the triangle. It is a very old-fashioned tool. It does come from kind of ancient Greek kind of era. It's often referred to as Heron's formula. Technically, it's Horon's formula, but everybody calls it Heron's formula. So Heron of Alexandria, great geometer. But he developed this formula for the area of a triangle if we just know the side lengths. Now, it's very possible to use law of cosines to figure out this other angle. We know that the a squared equals b squared plus c squared minus 2bc times the cosine of that angle, angle A. So we could find that angle A, and as soon as we have that angle A, we could use our tool for area that we've been using. But they didn't have that back in ancient Greece. Trig was not, either popular or sophisticated around there. I think it coexisted with that in India at the time, but I'd have to check my dates. But anyway, that tool wasn't available to Haran, so Haran didn't use it, and had this nice formula for area based on just side lengths. It is kind of computationally heavy, but it doesn't involve any complicated tricks. So it's a nice tool to know that it's around, but if either you don't want to, you're okay with a little bit of approximation, prefer the trig, for whatever reason, you can always calculate this angle and use the 1/2 BC sine A tool for area. But it is a nice tool to know how to use. So it is kind of a weird little formula because it does come in two parts. It is the square root of the product of s minus a, s minus b, and s minus c, and those are our side lengths a, b, and c. But what's this s? Well, where that s is equal to half of the sum of the side lengths. Now you're being presented with this formula without proof. I have gone through the proof of this, but it's long, it's horrible. It's kind of fun if you're interested in that sort of stuff. And, you can Google proof of Heron's formula if you want. But it's a little bit lengthy, so we're not gonna present the proof. We're just gonna present the tool here. But if we want to use it, we got to kind of calculate this s. So that s would be 10 plus 15 plus 7 divided by 2, so half of the sum of the side lengths. So that's, 22, 32 divided by 2 is 16. Yeah, that's a nice number. So then our area is the square root of that 16 times 16 minus each of the side lengths. So 16 minus 10, 16 minus 15, and 16 minus 7. Again, you're curious why, look up the proof. So 16 times 6 times 1 times 9. So 16 times 54. I don't know what 16 times 54 is off the top of my head. That's 108 times 8, so 800. Okay. I also want to check that. 16 times 54. Yeah. 864. 864. So our area will be that thing's square root. Square root of 864 is 29.4. 29.4. And I don't see units, so I'm just going to say square units. So it's not a bad tool. It's a lot of numbers flying around, but the tool works fine. And frankly, computing that with law of cosines and then using our 1/2 BC sine A tool is also a lot of calculations. So, either way we want to do it, we should probably do that just as an example. Or we could have done 10 squared equals 7 squared plus 15 squared minus 2 times 7 times 15 times the cosine of that angle. So 10 squared minus 7 squared minus 15 squared divided by negative 2 times 7 times 15 equals the cosine of A. I don't like negatives down there, so how about 7 squared plus 15 squared minus 10 squared over, just distribute that negative up, 2 times 7 times 15 equals, no, sorry about that, equals the cosine of A. Sorry about that. Wrangle the pooch. Now, I know I did something weird here. You'll often see, or sometimes see, law of cosines solved this way. It is essentially b squared plus c squared minus a squared over 2bc equals the cosine of A. It's kind of law of cosine solved for finding the angle. You'll see it sometimes written as a different formula. It's just this formula solved for cosine. So it's not cosecant, it's cosine. So if you happen to see that, that's all they're doing. I just took advantage and thought I'd show you that. So, but whatever, 49 plus 225 minus 100 over whatever 14 times 15 is. So there's a fair amount of calculation in there, but we can really make the machines do most of that if we're careful. So 49 plus 225 minus 100. Get that value, divide that value by the product of 14 times 15 is going to turn that into a nice 0.8. I'm going to keep some decimals here just to be a little bit more precise. 8286. And might be surprised that number came out so small, but remember it's a cosine value, so it should be less than 1. So we're going to do a little cosine inverse on that thing. So cosine inverse of that thing. Oops. Why didn't you let go? That's why. Sorry. And I get 34, I can say 34 degrees. So 34 degrees. And of course we get the second answer, which would be 326 degrees, and all the coterminals. But we know we're not going to use those. So 34 degrees. This is a nice 34 degree angle. And I'm not surprised that that's so small. This, the fact that these add to 17 and that's 15 tells us that these sides are pretty small on that one, or these angles are pretty small, and that angle is going to be a fairly big obtuse angle. So 34 degrees seems fine. But once we have that, it's a little more to have to do. But once we find that, we can use our other area formula, 1/2 7 times 15 times the sine of the 34 degrees. Sorry, I ran out of space there. I can make more. Sine of the 34 degrees. So 1/2 of, 105 times the sine of 34 degrees. So 52.5 sine 34 degrees. So 105 sine 34. Oh, I guess divided by 2, so it's 52.1. Anyway, 29.2 29.35 or 29.4 if we round it. 29.4 units squared, and that's the same 29.4 we got there. So either tool works. Just are you wanting to play with the angles and the trig, or are you wanting to play with just the side lengths and the big Greek formula? Either one will work. It'll get you the same answer, get you to the same place. So, a Chicago city developer wants to construct a building consisting of artist lofts, that's nice, on a triangular lot bordered by Rush Street, Wabash Ave, and Pearson Street. The frontage along Rush Street is 62.4 meters. Along Wabash is 43.5 meters, and Pearson is 34.1, though I suppose that 34.1 is right there. How many square meters is available to the developer? Now notice, I actually kind of like this, that it's not actually a triangle, but we're kind of approximating it with that triangle of frontage. This is really common. You'll often see problems like, hey, we got this big lake and somebody wants to approximate the area of that lake. Well, you built a triangle. You say, we find that triangle. So find these lengths and or these angles, and you can find the area of that triangle, which is approximately the area of the length of the lake. It's a really common tool to use nice little triangles to approximate, even if it's not quite a triangular shape. Now, we could use either tools here. We could use Heron's formula, or we could use the law of cosines to build the angle and use the other formula, as we've seen. They'll both get you the same answer. So, but this came right after our Heron's section, so we might as well use Heron's. So Heron's is going to be, we have to calculate that S. So half of the sum of the angles, 62.4 plus 43.5 plus 34.1 divided by 2. 70. Nice. 70. Oh yeah, that adds to a nice whole. Okay, fine. We're trying to give us nice numbers, I guess. So that's the MI perimeter. If you're curious why S, it's MI perimeter, half perimeter. And then the square root of 70, and then 70 minus each of the lengths. So 70 and then 70 minus 62.4, and then 70 minus 43.5, and then 70 minus 34.1. Notice we don't care what order they're in, which one's labeled A, B, or C. So square root of 70 times, what is it, 7.6 times 26.5 times 35.9. Hopefully I've gotten those right. If not, adjust them. So 70 times 7.6 times 26.5 times 35.9 gets us, a very big number. Square root of 506,118.2. But then square root that and get 711.4. 711.4 square meters. All right. That might seem like a lot, but if we imagine kind of a rectangle here, that rectangle, it, if I roughly approximate it, 30 by 40, that would be 1,200, and this is, about half that. So, it seems reasonable in scale. So it might seem like a big number. Areas always seem to get big. So Heron's formula, it does have a lot of crunching. The numbers do tend to get a little big, particularly before you square root them. But it works just fine. You might be able to tell I tend to prefer finding that angle and then using the other tool, but, to each their own. It is nice to have, this value can be a nice exact value. There can be a little less approximating involved, but not always. You can actually keep very exact going into the other formula as long as you're comfortable with the sine cosine inverse. Let's see, 30 minutes. Do you want me to do it the other way too? Yeah. If you don't want to see it the other way, stop the video. You want to see it the other way? Watch the video. So then the 34.1 squared would have to equal the 43.5 squared plus the 62.4 squared minus the 2 times the 43.5 times the 62.4 times the cosine of whatever this angle is going to end up being. So 34.1 squared minus 43.5 squared minus 62.4 squared divided by the negative 2 times 43.5 times the 62.4 is the cosine of A. So A is the cosine inverse of whatever this ends up being. And I hate that negative dangling out in front there. So I am going to reverse everything. 62.4 plus 43.5 squared minus 34.1 squared over 2 times 43.5 times 62.4. And again, this is one of the advantages of doing it without, calculating anything. Moving everything around like that's not, too hard to do when you're used to it. But, this is the disadvantage. Which are you more comfortable with? Dealing with the big numbers in the calculations or dealing with this kind of manipulation? Whichever one you're more happy with is probably going to determine which tool you like more. But 62.4 squared plus 43.5 squared minus 34.1 squared, all that divided by the quantity of 2 times 43.5 times 62.4. And that gets us a nice, just to have some parts here, cosine inverse of 0.8516. So then I'm going to take cosine inverse of that. And get 31.6. So 31.6 degrees. Now, yeah, we do have to use two different tools. We have to use two tools here, but a little different. But then the area of that triangle is 1/2 the 43.5 times the 62.4 times the sine of the 31.6, but we could even say the sine of the cosine inverse of the 0.8516 if we wanted to do less approximating, or even the cosine inverse of all of this stuff. Plug that in there, and then you're completely exact which is nice, but I think we'll just do the 31.6 here. Sorry, just the sine of that 31.6. But just to be clear, you can stay very exact if you need to. So 1/2 of 43.5 times 62.4 times the sine of 31.6 degrees. And should be no surprise, we get 711.2, that's fun, square meters. So, the approximation here and the little approximation we did there, did very little approximation. So this is probably more accurate. This, I presume I lost some in that approximation. It is 31.61219406, so on degrees. So my guess is this is more accurate. But if you wanted to carry more accuracy, that sine of the cosine inverse can do that. So, both tools work, and it's a nice, excuse to practice a little bit of your law of cosines. Anyway, so those are just a couple of neat tools for area to broaden your toolkit for area. There are lots of applications. I particularly remember a lot of problems coming up in Calc 2 and Calc 4 where using 1/2 base times height just makes a horrible problem. But if you switch it into angles instead and use the 1/2 BC sine A, then you get a really nice little way of solving a problem. So they do come up. It is handy, particularly that 1/2 AB sine C, or side cosine angle, or sine angle. Anyway, using that version of the area formula can be really handy in lots of applications. So it's a nice thing to kind of be wandering around with. Okay, have a beautiful day, and I'll hopefully talk to you again soon.